So post hoc comparisons. Last day, not last time we was talking about transformations. Last time when we talked about analysis of variance, I said that, remember that the null hypothesis is that two groups are different from each other. At least two of the groups. It doesn't say which two. Right? So you've got a significant F. Let's say you got a very simple experiment with three groups. What do you do now? Now, look, there is a philosophical position out there that says your hypothesis was two groups are different. Design your experiment such that I can look at the pattern of data and say at least two groups are different. I know which two it is, or which one's the different one, and I'm happy. And I am very sympathetic to that because my stats prof in grad school said that, and I kind of think of everything he says as being true. That said, it doesn't get you very far when most of the world doesn't think that way. So our HO is mu1 equals mu2 equals mu3 equals ... mu sub k. But which two means differ? So if you got three groups or five groups or eight groups, I don't know. The question then is which groups differ? Well, this is a way to do it. I'm going to show you or tell you about a series of different ways of finding out if you have different groups, like which groups are different from each other. The simplest method is called doing a t-test using what's called the Bonferroni correction. You read that Bonferroni? It's delicious. Joke. Funny, obviously, but it's the closest thing. Statistics isn't funny. It's deadly serious. We should all stop laughing. I don't know, maybe we do it. Okay. I'm waiting for this snowstorm to come. Not yet. Okay. Because it's been upgraded to a warning now. We're all going to die, I think. Ooh, boy, it looks like that doesn't look good. It's coming. All right. You can do t-tests, the alpha would go up. So what the Bonferroni correction does is it takes care of this by dividing. So it's 1 over n times alpha, where n is the number of comparisons you want to do. So let's say you want to do 3 comparisons. So you have 3 groups, and you want to do 1 versus 3, 2 versus 1, and 2 versus 3. What it does is it corrects the alpha level. It's really just a quick way of correcting the alpha level. And you might say, wait a second, then why wouldn't we just do 3 t-tests instead of the ANOVA? Good question. What if you got 17 groups and you really care about one, you care about, does the experimental group differ from one of the control groups? That's all you care about. So you do 1 comparison. Well, then you just do 1 t-test. Maybe you want to do 4. Yeah, maybe, I don't know how many comparisons you have with 17, but it's a big number. Maybe you just do 4 of the comparisons, okay? So that's why it just does that. It just goes 1 over n times alpha. So it's just a t-test. It's called t prime. T prime equals x bar 1 minus x bar 2 over the square root of 2 times the mean squared error divided by n. Mean squared error, well, mean squared error is the standard deviation is the variance, right? So the square root of that, it's a t-test. It's a straight up t-test. It's a 2-sample t-test. And then you look up to see if that t prime value exceeds the critical value. You don't usually look it up. You know how you do it? You click when you on SPSS, and you do a one-way analysis of variance, and you do a little click, and it says comparisons, and you choose the ones you want. Right? Here's another one. It looks very similar. It's called the studentized range, and it's called Q. It's the largest mean minus the smallest mean that you're trying to compare. Okay? Divided by mean squared error over n. If that number exceeds a critical value, then you say the largest mean is bigger than the smallest. Okay. That's pretty easy. It's not like this is complicated. And again, no one does these by hand. Literally nobody does these by hand because the computer's already done, already know it for you. So why don't you just click the post hoc comparisons? There'll be there's a comparisons thing in the one-way procedure in SPSS. How about the Newman-Cool's test? It's like everybody in like the 40s and 50s. Like, I'm going to come up with my own. I'll name it after myself, and I'll change one little thing. So this one's a little bit different just because of the way it looks. With this one here, you look up a Q value that has how big your range is, like how many comparisons you're doing. Are you doing one comparison, just two comparisons, three, whatever? And how the degrees of freedom for that, which is just going to be the number of subjects per group minus one. And then 0.05 because you always 0.05 levels. And then you take multiply that times the square root of the mean square error over n, and it gives you a value. And you look up the value and you see if it's I'm thinking about this one. Yeah, that's right. And it gives you this number, W sub r. Let's say it gives you 6 when you do this calculation. So you look all this stuff up, you look up this Q value, you've got mean squared error, you've got n, you now look this up, and you then get this W value, and let's pretend it comes out at 6. And that says any comparison where the means differ by 6 or more, they're different. Does that make sense? So like, if you've got 11 and 10 and 3 for your 3 means, that means 11 and 10 aren't different, but 11 is different from 3 and 10 is different from 3 because it came out at 6. Just gives you it spits out a value. And again, you wouldn't do this by hand. For some reason, we were made to do this by hand in second year when I was in undergrad. I don't know why. But it didn't teach me anything. So any set of comparisons within the range R, in other words, how many comparisons you're doing. There's another one like this called Tukey's HSD. You know what HSD stands for? Honestly, significantly different. Tukey was kind of like being a little passive-aggressive with the name of his test. No, my test actually finds significance, which I think is pretty lame. Funny. Tukey's just uses the biggest possible range. Okay, and that's just a couple of them. That's like 3 or 4, whatever the hell I did. There's a zillion of them. There's one called LSD, which I think was done just on purpose. Like I think you would. I'm going to call mine instead of HSD, LSD. Now what could that stand for? And it's least significant difference. You know, so I'm sure someone's going to come up with the THC test just because. Totally, honestly, completely different. Yeah, but we should develop that. Crowdsource that. So, which comparison do you use? Now, I'm not going to lie to you. This is what most people do, which is what you shouldn't do. And they just, well, let's do all of them and see which one fits my hypothesis. Oh, I hate that. But that's what people do. Me no likey. That really bothers me because it's dishonest. Right? It's like when you're a kid and you're playing a game and you say, okay, it's best 2 out of 3. Okay, best 3 out of 5. Okay, best 4 to 7. You keep going until you win. That's kind of what that is. It really bothers me. But that's what a lot of people do. I'd stick to one in a paper. I know that again, I've reviewed articles for journals, and I see that the postdoc test that's used changes experiment to experiment. And the comment I usually make is this because it didn't work with the other postdoc test? Could you please be consistent? Or it looks like, I wouldn't usually say that because that's really shitty. I'll say it looks like you might be doing this rather than saying you are a dishonest jerk. You don't do that. Even when you don't sign things. Reviews are blind? Well, all mine are. You know, people. In some journals now, you actually sign your name. You have to, which is kind of cool. I choose HSD because it's right in the middle. It's right between being conservative enough that it doesn't find things that aren't there and being sort of open enough that it's enough power that it finds stuff. So typically I use Tukey's HSD. I like that one. It's easy to do, and everybody knows it. There's so many of these that the problem you can run into is you write it in a paper and then you submit it to a journal or your thesis or whatever, and someone looks at it and goes, I don't know what that statistical test is. And then you have to explain it to them. Right? It's hard enough explaining to people what your methods are and what your results mean and all those things. But when you also have to explain, okay, here's how statistics works to people, it's not good. Right? Now, there are times you have to do that. For some stuff I've done, I actually have a weird statistic that I use sometimes, a log linear stat that is completely appropriate, but no one knows. So I always have to say, please see Sokol and Rolf's biometry, the chapter 16, for an explanation of how this statistic is distributed. And it's usually fine. But you don't want to be doing that when you're talking just about your postdocs. So I'd stick to one. Tukey's HSD is probably the most common. Newman-Cool's SNK, that's the student dice range. People use that. Bonferroni isn't used very much anymore. Right. This is not a huge deal, and that's why this is a very short topic. But it's something that once you do your thesis, for example, which is I think most of you guys are planning on doing that, you'll be asked to do postdocs. And even if you work with me and I say, it's not that important, what's the pattern of your data? Other people are going to say, why didn't you do postdocs? So I'll say, you should probably do them. Questions? What I want you to know from this is that these things exist and you can do them. I'm never going to ask you about the formulas, because I don't know them either. Unlike a t-test where I just know the formula. All right?